You guys know where the word Renaissance came from? Rebirth of what?
Well, it means rebirth. But the only way for something to be reborn or reborn again is had to be dead first.
So ironically, you could say that.
Yeah.
But what was being reborn? What had so-called died such that it was then reborn in that period?
Generally, like science or our notions of science, I guess, and how we thought of each other and like human beings.
Fundamentally, there's a core idea of human nature that was embedded in Socrates and Plato, in the greatest science, that had been lost for over 1,000 years. After Athens went into an imperial mode and shut down its appreciation for the ideas of Socrates and the ideas of the school of Athens, when it had been taken over and was subjugated to its own self-destruction by losing a love of truth. The whole of human civilization went into effectively a dark age. Great revolutionary ideas didn't really happen, except at a certain point in Islam, you did have a grouping of humanists who did tap into that, revived this lost idea, gave birth to it, and through this process you had people like Cusa, who, coming from Europe, from Germany, was living in a world of complete oligarchical terror. There was just Eastern and Western churches killing each other in civil wars, and all being funded by the same Venetian bankers for hundreds of years. That was the way of life of the Dark Age. It was just literally constant death through famine, disease, the pest, and war. And a lot of ignorance, like Christine went through at the beginning of her presentation. So when Cusa actually went and organized in Constantinople, he discovered that within the matrix, the cultural matrix of the Islamic Renaissance, there was this breadbasket, this amazing discovery of this lost method of thinking that had the idea that man was not an animal or a worm to be, whipped for causing a dark age. There was an idea that there was actually something divine within every human child. And this is something that he and a network of co-minded thinkers brought back and made the struggle of educating the orphans, of creating an idea of natural law, that every human being, regardless of race or gender or whatever, had the capability of discovering universals and applying those discoveries to improving the lives of themselves and their fellow man, both now and into the future. So, Cusa was a major, most people here probably I didn't hear about Cusa. I'm guessing people who haven't already been around the organization, I'm guessing people have not heard about Cusa. Am I wrong in assuming that people who have just come here for the first time have not heard of Cusa? Nicholas of Cusa? No, probably, you haven't heard of him, right? No. Me neither. And this is probably yet still, like LaRouche makes the point that Cusa, along with Brunellesc, gave birth to modern science, the modern nation-state system, the idea that the feudal will of an oligarch, of a lord or a monarch, is not legitimate to rule the masses. Right? That everybody has within them the ability to, because they can discover the laws of creation, they also have, when they discover those laws, when they're given that opportunity to develop themselves, the ability to judge and give consent for what laws govern their own society. The idea of self-organized nation-states came out of this fight. And it wasn't just given to us by an oligarchy that wanted a new challenge because they were getting bored and it was too easy to control people. So, what LaRouche stated in a somewhat recent paper in 2007, when describing this process that I'm going to unfold, he said, for modern civilization, the first crucial experimental test of Cusa's principle for the modern practice of physical science as a whole came with Johannes Kepler's uniquely original discovery of the principle of universal gravitation. The significance of Kepler's discovery of this principle of experimental method and his ensuing discovery of the harmonic composition of the planetary orbits typifies the notion of universal principles which should have guided modern European science thereafter. So that's a lot for one sentence, or two sentences. But this is going to become a lot more clearly developed. I'm not going to go through the full implications of Kepler's discovery, but I'm going to go through some elements of this. First of all, I don't didn't know Cusa, but do people here generally know Kepler, Johannes Kepler? Heard of the name? Anything? Of course. Have you heard of Johannes Kepler?
Yeah,
A little bit? Eve? Yeah, of course. Yeah. Okay. So what do you guys know of Kepler? What do you know when you, so what do you associate with the word Johannes Kepler?
just what's told.
Just what I told you. Eve, what do you know of Kepler?
That he was the father of the notion of gravity.
Father of the notion of gravity, yeah. What did they usually give you when, I don't know if you remember back in school days?
They gave us formulas.
Formulas. It's 3 laws, right?
Is there the story about an apple?
No.
That was a guy 80 years after Kepler, who we've made the very provocative statement ripped off. It was actually a political plant to rip off all of the real discoveries that Kepler made, and Leibniz made, and Huygens made, and Bernoulli made before him. That guy's Isaac Newton. There's a big myth around him being this like godly, like universal genius who discovered everything through empiricism and mathematics and didn't use his. He actually put out a law of mind saying that if you want to make discoveries like me, if you want to be as great as I am, you just can't make any hypotheses. You just use your senses. You make formulas to describe what your senses tell you, and maybe you'll get it kind of approximately right. Now, that if you actually adopt that method and use that, because it's so great, you want to be great and make further discoveries. If you actually adopt that method, you're actually not going to make any more discoveries, which is something which we can go into.
It could be said that the only time Newton really used his head was when he received the apple.
Yeah, there's a rotten apple there. Let me just write on the board. I guess I'll just write. So just, what we're given is the shell, right? We're given the 3 laws. You remember what those 3 laws are? Kepler's formation. They're basically formulas associated with describing ellipses, right? He's the guy, after all we know, was the first to conclude that planets don't travel around perfect circles. They travel in the form of an elliptical shape around the sun, right? So there's certain formulas associated with ellipses, which have 2 focal points, and thus, you can apply those formulas to calculate motions of planetary bodies in space. One of those focal points is the sun. He discovered that there's a quality. We're usually told the second law. I'm just going through what we're told in school, right? This is not saying why these things are true. These are just saying what we're given, and then we're told to just memorize that and maybe use it if we go become mathematicians. He basically discovered that there's equal areas and equal times. So area, time. So if there's a certain given area swept out at the maximum distance, at the closest distance, over like a certain x time, and you take that same amount of time at the furthest point that the planet is from the sun, right? So I'll call this A and call this A prime. That same amount of x time that the planet sweeps out at the furthest, as you see it in the closest, that area of A will be equal. Okay, so this area will be equal to that area on the condition that this time is the same as that time. If that's true, you get equal area, equal time. And the third thing is something which we're not going to touch on so much in this presentation, but that in every planet, there's a square-cube relationship. Now, we're usually given these numbers as numbers. We're told, like, just add a little 3 or a little 2 on top of the number, and you get the square and the cube. Kepler doesn't think numerically. He uses that, but his point is always think physically. Think about actually the purpose of using volumes and squares to measure areas and volumes. Don't use cubes, right? Don't think of it just as being numbers. So the period squared of any planet has a certain relationship. To the cube of the average distance of the sun. So if you take the average distance that any planet has to the sun on its orbit, cube it, you'll get a certain proportion to the square of its total, 1-year cycle. The time it takes to go right around that sun from beginning to end, cube that, square that, you get a relationship. Now we're told that these are things he did, and we're told pretty much within the next breath, now we're going to go on to something completely different. LaRouche's point is that this is the most superficial component to what Kepler actually did, because it's more about, if you have the choice of getting into the substance or the form of anything, what matters more before the form is to get at the substance. What did he actually do? What was his mind doing such that he was able to discover those qualities of our solar system? And LaRouche makes the point that you got to go to somebody who influenced Kepler a lot, and that's Cusa. You got to investigate Cusa because Kepler cites Cusa. And I'm going to go through one citation. Because the way that we currently treat mathematical models in science today is only moving us further and further and further away from actually making real discoveries of principle. And you can get that from the fact that just look at every model that's trying to project the future of the economic system has completely failed. Every long-term projection by a mathematical economist to try to project where the economy is going to go has failed. Nobody forecasted any major collapse of the banking system. Anything that's occurred was not in the models. It wasn't pre-programmed into the formulas, part of the models that extrapolate trends from a certain sliver of time. Same thing for climatologists. Every single projection of every climate model that we have never predicted the 16-year, what do they call it, the pause. The global 16-year global warming pause from 1998, where warming has just stopped. None of the models had predicted that. After the fact, they tried to explain it away, but nothing was able to predict that. So no matter what type of models, and there's infinite flavors of models, none of them are able to actually work when you apply them to discovering physical reality, except LaRouche's. What LaRouche has been doing for the past 50 years in generating long-term forecasts on record have come to pass. So there's something very different that's not mathematical or statistical in its nature that LaRouche has been trying to explain that people have to understand. That has more to do with astronomy and what you can learn in investigating astrophysical principles than it does about monetary or supply and demand theory or anything like that. And you can verify that. So, when you go to Kepler, this guy he basically had a lifelong devotion to truth. We're going to say a few words about Kepler after we read this. Or no, before we read this. Kepler, you got to keep in mind, this is a guy who was born into a world of religious warfare. Protestant versus Catholic warfare. The 30 Years' War was waging. Again, everything that the Renaissance humanists had tried to accomplish by breaking the world out of the Dark Age had been under attack almost immediately. Everything Da Vinci was doing was under attack by the oligarchy to bring back the old system of feudal controls. And the best way to do that, when you can't beat them in argument, you just launch a war. So there had been 100 years of just constant war that Kepler was born into. His dad was a mercenary. His dad died as a mercenary in one of the many Venetian-sponsored wars in Germany. His mom was tried as a witch. She's probably a pretty smart lady. By the Inquisition, right? Kepler he spent years defending her life and succeeded. He himself was born quite a frail child. And he had bad eyesight. He actually didn't see very well. He had eyes like, almost, as far as I've heard the descriptions, almost as bad as mine. Which means he couldn't really see the stars. However, in spite of all of these obstacles, he was able to devote his life and generated probably the most significant potential to break the oligarchy in the longer waves of history. Maybe not while he was alive, but in longer waves of history, what he did actually provides us the best means to break away from the oligarchy's systems that we know of. Now Kepler, writing in 1596 in his first works that were published, the Mysterium Cosmographicum, wrote, Luke, you want to read that?
Now God decided that quantity should exist before all other things, so that there should be a means of comparing a curve with a straight line. For in this one respect, Nicholas of Cusa seemed to me divine, that he attached so much importance to the relationship between a straight and a curved line, and dared to liken a curve to God, a straight line to his creatures. And those who tried to compare the Creator to his creatures, God to man, and divine judgments to human judgments did not perform much more valuable a service than those who tried to compare a curve with a straight line, a circle with a square.
Now, that's not the most scientific language you would imagine when you look at a great scientific mind. You wouldn't expect those types of words to come out, right? Because you got this idea today in science under empiricism that
What did he say?
today under in empiricism.
No, what did he say though?
I'm going to talk about that.
Okay, sorry.
Yeah. I'm going to let it just boil over a little bit. You got this ideal in the current practice of mathematical modeling that the human subjective element, which has metaphysical notions, emotional concepts, things that are pollution really because they're subjective. They're not absolutely objective, cold, hard facts of formulas about the universe. We shouldn't let that contaminate our objective empirical pursuit of facts about nature. We should keep them as separate as possible. Now that ideal, which is a relatively new ideal in the grand scheme of things in science, is artificial. And in fact, had Kepler adopted that view, he wouldn't have been able to carry forth his lifelong investigation that bore those discoveries. And had he used the view that, we all have this view, right? Reason is what? What is reason? Because if we're going to come to know truth, we have to use reason. What is reason? How do you define its behavior? So we get this idea of logic, right? Deductive, inductive reasoning. You start with sense, either you start with sense perception, and you start accumulating facts, and you just see if there's patterns that form in the facts over time. Or you go the opposite path, and you start with some basic abstract rules, and then you use those rules to start. You just assume that they're true. Whether you prove them or not is irrelevant, like Euclidean rules that Christine went through. It doesn't matter. You just start with those rules, and then using them, you start plugging in data into those rules. Mm-hmm. Either way, if you just make conclusions based on either one of those two methods, you couldn't make one of these actual discoveries, because Kepler is getting at that there's an idea that he got from Cusa, the divine Cusa, regarding Cusa's work on thinking about the idea of the creator, because you're investigating the universe, which has been created. Obviously, there wouldn't be a universe if there wasn't some process of creation happening. I mean, there's a cause to any effect. So in his mind, he's thinking, okay, well, probably not a big bearded guy in the sky, right? That's probably not his idea of the word God. So let's just throw those crazy ideas out. But he's got a much more, much higher idea of God. And it's the creation, which he's saying is our obligation to investigate. And he's saying Cusa used as a way to try to get at that, the idea of the curved and the straight, and the idea of human judgments to divine judgments as being something which you could think about by investigating curvature and straightness, a circle with a square. Now, what does Cusa actually say? So go back 130 so odd years, and you get a very important writing that LaRouche has been citing for years, called the Deducta Ignorantium. And this is what LaRouche has always been stating: people have to immerse themselves in an investigation in this work, which formed the basis of modern science. Every great discovery that happened had at its heart the breakthroughs, the epistemological breakthroughs found by Cusa in Deducta, which simply means unlearned ignorance. How does the mind come to learn what it's ignorant of? Right? How does the mind bring itself into the investigation of something which it's investigating? So don't separate yourself from the process that you're investigating. Include your mind in the process. And if you don't do that, you won't be aware of the blind spots. So Cusa says, whatever is truth cannot measure truth precisely.
Start again.
Okay.
Sorry, not true.
Oh, that would have changed everything. Okay, lost enough over.
Whatever is not truth cannot measure truth precisely. By comparison, a non-circle cannot measure a circle, whose being is something indivisible. Hence, the intellect, which is not truth, never comprehends truth so precisely that truth cannot be comprehended infinitely more precisely. For the intellect is to truth as an inscribed polygon is to the inscribing circle. The more angles the inscribed polygon has, the more similar it is to the circle. However, even if the number of its angles is increased ad infinitum, the polygon never becomes equal to the circle unless it is resolved into an identity with the circle.
Now, does Cusa mean that the universe is the circle? We're like literally like lines or like squares inside the circle having sides added to a polygon? No. No, he's not a literalist. That's not literally true. He's a poet. Cusa's looking creatively for what type of metaphor would help us understand an incommensurable. Right? That if you try to mathematically describe something perfectly that couldn't be made any better, kind of like one of Aristotle's definitions, which are just, he's looking for these perfect definitions of justice, that if you read one of these things, you're not going to be able to add anything to it. He's just like trying to give you this complete crystallized object of a definition that you have to take with you and carry with you, and that you can't add on. You can't discover something better, or discover even that it's wrong. If you have that idea in what you're trying to do in discovering something about the universe, to discover it perfectly, what Cusa's getting at is that you're actually going to fool yourself. You're going to be like you'll always be trying to I won't say add more lines to the circle, but you're always going to be attempting to approximate something which can't be known that way. Because if the universe is always in a state of change, it's always if the nature of the universe is constantly changing in a direction, qualitatively as well as quantitatively, then you can't just apply some logical, linear thinking to something non-linear. It's not going to work. It'll be what he calls a non-circle measuring a circle. You can only measure a circle with a circle. You can only measure a line with a line. You can't. You need something like the other thing that's being investigated. So he's got this example here of the metaphor being described in this nice geometric pattern, where he used the idea of the circle being truth, and the intellect, that which can logically, formally know something, as the polygon. So while it might seem as though you're always adding more to your polygon, the more evidence, the more facts you add to your model, it might sometimes approximate ever more closely to the circle. Empirically, it looks that way. If you add like 1,000 more edges to the polygon, you're not going to see a difference between the polygon and the circle. With your senses. But is it actually becoming more like the circle, or is the polygon becoming more unlike the circle?
More unlike it.
More unlike it.
Because it's got more angles.
Exactly. So if you move out of your senses and into your domain of understanding, how do you define a circle? A circle is defined as that which, what? How would you finish my sentence? Circle is, how would you define it, guys?
No angles.
No angles. Right? All agree with that? It's a shape which is equidistant, you'd say? It's equal distance from the center. And has no angles. Right? It's constant curvature. But then a polygon with a million sides, does that polygon have angles? Yeah. If you have a billion sides or a trillion sides, it still has. So you're actually adding more sides. You're moving yourself further away from the essence of the circle, which has no sides, right? Just curvature. But you're fooling your senses. Your senses are being pulled in the other direction. So there's a dichotomy. So this is a concept. This is a necessary concept that Cusa and Kepler both utilize in their exploration of the nature of physical spacetime. There's a second element to this that will affect how we investigate what Kepler is doing in his investigation. I'm realizing now I'm not going to get through half of what I wanted to get through, so that's okay. We're still going to get through some good stuff. Cusa points out later on in the work, moreover, it is no less false that the center of the world, the universe, is within the Earth than it is outside the Earth. Nor does the Earth or any other sphere even have a center. For since the center is a point equidistant from the circumference, and since there cannot exist a sphere or a circle so completely true that a truer one could not be posited. It is obvious that there cannot be posited a center, which is so true and precise that a still truer and more precise center could not be posited. Precise equidistance to different things cannot be found except in the case of God, because God alone is infinite equality. Therefore, he who is the center of the world, that is, the blessed God, is also the center of the earth, of all spheres, and of all things in the world. Likewise, he is the infinite circumference of all things. So again, you're getting back to this idea of, do we live in a universe of change or no change? If the universe is saying, if you were to conclude that the universe is filled with spheres, like the Earth, that are perfect spheres, incapable of being any better, well, that says something actually about the universe. If there were possible any type of shape, whether the orbit of the planets or the shape of a sphere, that couldn't be made any better, that puts you in a universe which is incapable of changing. If a state of no change could exist. And that's a pretty big problem. So he makes the point that even though it seems as though here we are on the Earth, oops. Oh no. Oh man, there's something else fast. Okay, what is it? Okay, so there's some slides I didn't include on this next step. Now, if you just stand on the on the surface of where we are here on the Earth and you look out, what shape does the universe appear if you go out to the night sky and you look around, you try to guess what shape is the universe from you're 400 years ago now, early astronomer looking out. What shape does that night sky of stars look like?
It's like a sphere.
Yeah, well, it looks like a sphere, right? It looks like a giant sphere. It looks like that sphere is moving around you, right? It doesn't look like you're moving very much. It looks like you're fixed and everything's moving around you. Now, Cusa, this is already back in 1430. Cusa makes the argument in this work that would be epistemologically absurd, that we could be possibly in the center of the universe, even though everybody thinks that way. Most people in his time did have that view. Because if we were in the center, then you'd be in it. If there was such a thing as the center, then the universe would be fixed. It would be a state of no change. This big, unchanging sphere would be governing change. The change that we see would be secondary to no change. Cusa says, no, that puts a big limit on your idea of God, as being something who created a universe but couldn't make it any better. This is picked up again by some people that we know, like Leibniz later on. Now, Cusa also says that if we look at Polaris, and he says that's the North Star, right? He says if you put yourself on as an observer on Polaris, looking down at Earth, the North Star, he said if you were there, it would appear to you that you were in the center of the universe too. And he makes the point that any part of the universe that you put a person observing the universe would appear that they are in the center of the universe. So the idea that the universe has external bounds is also absurd, because if you presume that the universe was this physical sphere, right, that has external bounds, that would also be absurd, because now you have to suppose that there's like a bigger universe containing that universe, or something that is not. If the universe is everything that is, you would have to conclude that there is now a bigger expansion of nothingness that contains the isness of physical space-time, which is again an absurdity. So he's really hammering this in a bunch of very scientific angles, but he doesn't have the experimental data, right? And he also makes the point that the Earth must be moving. He actually makes that point. But it's a good question for us. How would we say that we know that the Earth is moving around the sun, but how would we actually know that the Earth is moving around the sun? How would did we discover that in our mind, or is it just that we saw movies or we saw pictures and we were told that? Because it's actually not so easy to conclude how the mind of somebody 500 years or 600 years ago would have come to that conclusion rigorously and proved it without ever having gotten off the surface of the Earth. So again, these two concepts, that perfect geometry can't exist, it's an ontological absurdity if you suppose that in your model, and that you can't remove the idea of you as a scientist or as a human being exploring truth. You can't remove yourself from that which you're exploring, because you're made also as part of the universe. But you're the smallest part of the universe, but you're the biggest in another sense, because you're the only part of the universe that can think about itself thinking. No other part of the universe that we know can self-reflect on itself. That's interesting. Animals don't think about the universe. They don't have that idea, right? They live in these little intervals of time. So again, Kepler, like I think this is a citation from Christine's presentation. Kepler again stated, God, like one of our own architects, approached the task of constructing the universe with order and pattern, and laid out the individual parts accordingly, as if it were not art which imitated nature, but God himself had looked to the mode of building of man, who was to be. That's a strong hypothesis. It doesn't mean that's right, but that's a strong hypothesis that he's using about what the nature of the creation that he's going into, which includes himself. So again, you're in the middle of the 30 Years' War. Chaos is raging. Death is everywhere. Your dad just died as a mercenary. You're thinking, how am I going to change things? How am I going to devote my life to something eternal when everything is so fleeting in the finite world that I live in? And so Kepler looks up in the night sky, and unlike a lot of people who are doing the same thing, he has conviction that there's something ordered that needs to be discovered, that he has the ability to, he's not wasting his time. He has the faith that he's not going to waste his time in the next 30 years of his life, where he devotes it to the same question, right, consistently. And don't think that he's living in comfort in an ivory tower. Like, this guy is eking it out, like, day to day, fighting to get his ideas heard, fighting the Inquisition. This guy is, like, not being sponsored by, like, the oligarchy at all. He does have people sponsoring him, but he's not living a life of affluence like you have with Newton or Galileo or some of these empiricists. So he's looking up at this seemingly chaos of the night sky, and he makes the point in his new astronomy, which is the only part I'm going to look at today, that the testimony of the ages confirms that the motions of the planets are orbicular. It is an immediate presumption of reason reflected in experience that their gyrations, their circular motions, are perfect circles. For among figures it is circles, and among bodies the heavens that are the most perfect. However, when experience is seen to teach something different to those who pay careful attention, namely, the planets deviate from a simple circular path, it gives rise to a powerful sense of wonder, which at length drives men to look into causes. So he opens up his investigation of new astronomy, which is the book that features eventually his discovery of how he made these two first laws come to light, how he brought them to light. By first defining science is not a field of explanation, because that's what you get today, right? People say, oh, science can tell us how things work, but not why things work. It can't tell us the cause of things. It can just describe the effects and the mechanics behind effects. The causes, don't try. Kepler doesn't have that. So he brings about the idea of wonder, because it is, it's a magnificent sight to look at the celestial sphere overhead, and that wonder, which brings the fact that you're thinking about this whole universe into one idea, the finite and the infinite, right? You've got these two opposing, very contradictory notions, but that are being brought into one because you are finite and you're looking at this infinite expanse, and you're moved to wonder. Unless you're unimaginative or you're broken down under an imperial system, then you just feel like, oh, that's proof that I'm meaningless. And I'm a speck of dust that has no meaning in the greater void of the universe. If that's the lesson, you should read more Kepler, which is usually the lesson people get when they're smoking a doom in a car in a field somewhere, right? That's guy. So he says, okay, experience and a presumption of reason, these things that provide to us the assumption that the planets are orbs, they move in perfect circles, and but sometimes they deviate from their simple circular path. So where do the ideas of circles come from? Well, that's something which has been present as an idea for anybody who's tried to map out the motion of the stars in the night sky for thousands of years. It's been known that there's a time-lapse photograph, but what you have are concentric circles, which if you're looking at Polaris, and you're just mapping out the motion of the planets, of the stars around Polaris, you start getting these concentric circles over time. But then what's causing that is because, again, the whole, universe is moving around us, or is there something else going on? Again, not self-evident. We're not, like JP was holding onto his chair there. You'd think that if we were moving, we would be also flying off our chairs, versus flying to outer space. So again, empiricism tells us that we must be fixed. Well, where's the deviation that Kepler describes? He says there, planets deviate from a simple circular path. So let's look at one that's not a planet. This is actually the sun. So one example of deviation is the second motion. So this is what's called the first motion of a planet or a star. Is simply just watching it and just following it, right? Over the course of the night. Constant, continuous motion. That's called the first type of motion. But over time, it became realized that if you take note of the position of one or another star in the night, let's say in this case it's the sun. So we'll use the example of the sun. If you take note of the position of the sun at a given time during the day, I think at this point it's 12 o'clock, noon, don't know where, I think it's Iceland. So you take a picture of it at one part of the year, and every couple of weeks you go back at the same time at noon, take a picture of where that sun is located, and you start getting this very interesting effect over the course of one year. They call it an analemma, I don't know why. But essentially it looks like a bowling pin.
Each year?
Yeah, this is 1 year. Yeah, so the course of 1 year, it's called the second motion. You can do the same thing with a planet, right? In the case of, so you get this very interesting geometric pattern which will occur, but not in the same place, because you do the same thing next year, right? 1 year goes by, you do the same thing over again, now it's going to be over here, right? 1 year's going to be over here. So it won't be moving the same rate of change. It won't always be in the same place. And the planets that Kepler is referring to, he's referring to Mars. And that's the purpose of the entirety of the new astronomy, is the investigation of what the hell is Mars doing. Because that's weird. When you use the second motion, there's another name for it. But you do that now to Mars over the course of 1 Mars year, which is about 687 Earth days. That's how long it takes Mars to do one rotation around the sun. For about a 2-week period, every 687 days, right, you're taking note of where it is in the backdrop of the zodiac behind it. So you're taking note of its position. And all of a sudden, for about a 2-week period, you'll come back one night, and all of a sudden it stopped moving in the direction it's been going the whole 2-year period, the whole 687-day period. It just stops. And then the next night, it's still there at the same spot. And then the next night, it's all of a sudden going in the opposite direction. And it does it again. And again. All the way to the point where you think that it's going to now just all of a sudden change course. Is now all of a sudden Mars just like moving in the other direction. But then, at a certain point, it stops going in that direction. And then it goes back onto its proper path that it had been doing previously for the 687 days. Okay. That's an anomaly. That's really weird. Especially if everything is perfect circles. If everything is really just perfect circles, whether we put the sun in the middle, or whether we put us in the middle, or whether we put Mars in the middle, you can do whatever you want, really, as long as it fits the observations. But if it's perfect circles, and everything is moving in constant motion around some point on the perfect circle, that can't be described very easily. It'd be really hard pressed to try to explain away that phenomenon. So Kepler does. Kepler tackles that. But first, the problem is he can't just go and tackle that, because people have explained it away mathematically. And pretty much any astronomer is told at that time that if you want to go into astronomy, you have to adopt one of these pre-existing standard models of astrophysics. You have to adapt to one of them. And the big three, maybe there are more, but the big three that were prevalent in his day that he tackles, there's 2 of them. Probably heard of Claudius Ptolemy, right? An old Roman astronomer who, there's reason to believe that he also, like Newton, ripped off most of the discoveries that he's attributed for having discovered by the Pythagoreans and by Plato. nonetheless, he had his prevalent model, which was the dominant model, and you had a new upstart more recently, born after Cusa, right after Cusa died, Copernicus, who had his model. A lot of people were beginning to use that, but that was still pretty controversial. Right, where Ptolemy, has the Earth in the center of his model. Copernicus has the sun in the center, kind of his model. There's another one which I'm going to show you an animation of from one of our science team members who put together this really great animation to just demonstrate. There's a third one that I'm going to show you, which is really far out there, but it was still somewhat popular in his day. The thing is, these are not exactly in the center. When you look at the Earth being in the middle, and you look at the sun being in the middle, as you can see from these diagrams, it's actually not the Earth. The Earth is just sort of placed there as an ornament in the model. If you look at the center in the Ptolemy system, there's actually several. The center for Mars's orbit, because Mars has one circle, its center is right there. The center for Mercury's is right there. So every black dot is the center of one of the known planets. Earth is just sort of there, it's not moving. The sun has its own. But it's not even the center of the orbit, right? It's not that the orbit, it's not the planet itself that's moving on the circle, which has the circle center there at one of these black spots. It's not that at all. What are these things? Have you guys seen these before? Yeah.
Those are are you saying that's their own orbits?
These are the orbits
Yeah.
around the, whatever it is, Earth, or the orbit around the sun.
But like as
With these little circles here that are red.
yeah, as it spins in the greater one, it spins on that smaller one?
Yeah.
Okay.
Yeah, so you have a little circle, and all the sizes are different, but these little circles have that's what the planet moves on. So as the circle itself goes around, or as the planet goes around this little red circle, its center, which is a point of nothing in the middle of space, which is a mathematical point that was created for the sake of making your formulas easier to work with, is being organized by this invisible spot, which itself doesn't exist either. It's just a mathematical spot put there because at that spot and at that spot, you can artificially pretend that there is constant motion, where motion is not increasing, accelerating, or deaccelerating. It's just from those mathematical imaginary spots, you could say that that's where constant, no changing, movement is happening. Copernicus too, the same deal. Like people celebrate him, and it was ballsy what he did. Fundamentally, he didn't put the sun into the center of his system at all. Again, he's got these several red dots that represent the same fundamental thing as you saw with Ptolemy. And those dots, like the Earth, actually Earth gets more complicated, but because Kepler criticizes Copernicus quite a bit, saying, look, all Copernicus did is he placed the sun there. It could be taken out, but he added one more epicycle, these are called epicycles, to conform to the model. So he has the Earth going around a circle, going around a circle, going around another circle, and none of these circles are going around points that exist. So that's a really lame explanation for the causes of motions. However, as we're going to see here, yeah. Oh yes, Olivia.
These models are a great example of what we can do with mathematics.
Mm-hmm.
In the fact that they work. Like
Yeah.
visually, it kind of explains what we're seeing.
Yeah.
And we can fit a mathematical equation to what we see. But it doesn't explain why we're seeing that.
Mm-hmm.
It's just we get a lot of that in physics today. Just mathematical equations that it works. We're good with that. Just like thermodynamics, that's exactly what it is. Thermodynamics is just taking a whole lot of data and making a system work so we can repeat that system again.
Yeah.
But thermodynamics doesn't explain at all. It's just
Yeah.
just like that. It's exactly that.
Yeah, exactly. Yeah, you're basically taking a localized phenomenon of something that you get from looking at a heat engine slowly running down, and now you're just going to universalize it. See, that's the whole general universe operates with that localized empirical mode of action. Thus, the whole universe is slowly dying, increasingly. That's a bit of a leap.
And that's blocking people into a paradigm. It's like a forced paradigm.
Yeah, there's limits to growth. Obviously, we can't keep on growing because every time we grow our population, that means we're just sucking energy down from some other part of the universe because there's only a fixed amount of energy to be distributed around the universe. So the more people there are, the more the economy is growing. Well, that's going to be increasing the entropy in the universe in some other place. So let's stop doing that. Let's just try to go for zero growth. Let's even shut down what we do have a little bit here and slow down the entropy. They don't even think they can stop the entropy. They're just saying, let's just slow down the death of the universe, which is ultimately like...
So just how Kepler is going to show everyone that Ptolemy and Copernicus models are fake and are bullshit, we need a Kepler today to show everyone that thermodynamic is bullshit.
Exactly. And this is actually a good, quick animation that Jason Ross had put together a few years ago, which very, it's very good because it can really just demonstrates very well that even though the Copernican, the Ptolemaic, which has the Earth in the center, and what's called the Bracheian system, they seem different. They seem like totally different models. But as Kepler demonstrates, they're actually describing the exact same thing. So the actual motion that you're observing as a point of as an observer, looking at Mars and looking at the sun, moving over the course of the year, that process, right? You even got your little retrograde motion there. You saw that red just do a little backflip. You're going to see it again when they're in opposition from each other. So when the sun and Mars are in opposition, Mars does a little backflip there. And this is where you get the epicycles. The reason why they needed these epicycles was because that's what would allow that mechanism was necessary to describe that observational anomaly. So you had to do that. Otherwise, you couldn't explain away the anomaly. So
I just wanted to comment on that because we're saying this is mathematics, but this is how people think about everything and in general. This is for anybody who hears LaRouche or reads what's coming out of our EIR publication, what's being attacked all the time is deductive thinking, it's mathematical thinking. Because this is a way of thinking. It's not mathematics, just the formulas we have in our head that we think back to in high school or CGEP or university. But people see something in the real world, they come up with an explanation, and then they're satisfied because they came up with an explanation that can explain what they're experiencing. They don't know if it's true or not, and they have no means of testing it. But it's just this mathematical way of thinking where if you can, deductively argue, well, this is happening because so-and-so, and it seems to make sense, you don't go any further. So you're just, going to be stupid forever.
Ecology.
Everything.
Everything.
Trying to make everything fit.
It's called being practical.
no, exactly.
Just being realist.
J'ai une question juste.
Oui.
Dans la même lignée de ce qu'il a dit. Là, ce dont on parle de Kepler, à la base, c'est quelque chose de scientifique, right? C'est pas juste une approche philosophique, mais LaRouche, en parlant de Kepler, et aussi Harley, quand il a parlé de Kepler, il dit que ça nous aide comme leçon et donc à apprendre qu'il ne faut pas s'arrêter aux axiomes et qu'il faut élaborer des hypothèses, n'est-ce pas? Et c'est pour cela que Kepler a pu élaborer ce modèle-là assez développé, disons. Mais d'un point de vue scientifique, c'est pas ça le modèle qui a inspiré les scientifiques, disons, pour élaborer les sciences modernes, right? La résultante de ce que l'évolution des sciences nous a amené, c'est ce qu'on connaît aujourd'hui, les sciences modernes. Donc, d'un point de vue scientifique, on ne sait même pas ce modèle ou cette pensée, elle nous aurait amené où de nos jours. On ne sait même pas. Si on devait s'arrêter à cette méthode de partage, juste pour un exemple, si on devait dire que, par exemple, deux lignes parallèles, se peut que ça se recoupe, ce n'est pas vraiment des lignes parallèles comme on les perçoit, et que aussi le mouvement circulaire, c'est peut-être différent de la manière dont on les perçoit. On n'aurait pas peut-être construit des immeubles, et regarde les ponts par exemple, on les construit de façon parallèle, les étagères de façon parallèle, et tout ce qui... Voilà.
but look, you don't want to mix up mechanics for epistemology, because when you're dealing with the idea of parallel lines, geometry, these are very useful concepts. The cube, right? The sphere. We use these geometrical ideas in their idealized fashion, right, to craft our world, our architecture, and everything else, as much as we can, right? This building would collapse if everything was at 89-degree angles instead of 90-degree angles, so it wouldn't last very long. So that's useful. However, the problem is when you start to generalize something practical into a universal, and say the universe is thus a perfect sphere of no change, just like this little sphere globe on my table might be, that's where you get a problem. You don't want to take empirical usefulness and just generalize it and say that that's universal. And that's a leap you don't want to do. Right? That's what Kepler's just saying. You don't want to make that leap. The point, though, that you were getting at with the evolution of science, which we can get at more in the discussion, that there's not just one current of Western science, so-called, from Cusa to Kepler to the moderns. There's not just one current. There's two opposing currents that are not in harmony with each other. You have that which sprang from the method of discovery. Go on.
But can you give me a practical, current example of two contradictory methods? One inspired of.
I can do that, but let's do this. Let's continue the class till the end. I can round it out. I can probably end this thing pretty quickly, and then let's have a discussion about that.
Okay.
After going through that, yeah.
The speaker. You put the speaker.
Yeah, I was going to, I was going to play the video, but the video's not working, so it's. So after he establishes that all of these systems, these models, are equally, are pretty much the same thing. It's the same model, and none of them account rationally for the reason why the planets are moving the way they are. He's then liberated to go to the next step. But before he does that, and I think this is worth just stating, this almost merits a whole class in and of itself, which I'm probably not equipped to give. So I'll state it in summary fashion. What Kepler then does, before he can disband with the idea of perfect circles and these mathematical points of invisible, no change around which things move, before he can throw that in the gutter completely, what he does is he creates his own model. He says he's gone this far, he's gone further than anybody else by proving that they're all the same thing. Then what he does is he says, for the first time, I will actually put the real sun into the center. I'm going to take the Copernican model, but instead of using some mathematical point, I'm going to use the real sun, not the average, so-called mean sun, the real one. I'm going to put that in the center, and I'm going to try to conform all of the data I have to fit properly into that new model that I'm going to create for the first time. And over the course of several years, he adjusts, he tweaks, he uses the perfect circles, he uses the epicycles even though he doesn't necessarily believe them. That's why he calls it the vicarious hypothesis and not his hypothesis. And what he does, I wish I had that video, but you can watch it later. What he then does is he says, okay, I've got it. He uses 4 observations of Mars, when Mars is at opposition from the Sun. So that means you've got pretty much Earth, the Sun, and Mars in perfect alignment. He uses 4 of those, and he puts them into his model, and he builds up all of the other observations that he has, and they fit. They fit one type of observation. Because when you're looking at a planet, that actually should be happier. So you got your little astronomer looking up. The thing is, when you're looking at a planet, let's do a little look around there, get the lake, okay, got some mountains. Okay, so you're looking at a planet. What you got are 2 different types of observation happening at the same time. So on the one hand, you have your, it's called the longitudinal motion, which is actually going this way. So you got your longitudinal motion of your Mars moving across what's called the plane of the ecliptic. I don't have to write that down. The plane of the ecliptic is simply the plane that you share with, it's a plane. Let's just say that. Forget plane ecliptic. It's a plane. You got Mars moving along an imaginary disk. You have your disk is what's called the plane of the ecliptic. The plane of the ecliptic is so you got the sun, you got Earth. The plane, the disk, which is shared, which is created by your relationship, Earth's relation to the sun, is called the plane of the ecliptic. Then you've got Mars, which has its own, which is not all on the same disk, right? The planets are not all on one flat surface. They're all bobbing at different latitudinal angles. So what you have here with Mars is it's going around, that's this action here, it's going around its orbit. You're observing it over time. And then you have two types of observations. You've got the degree to which Mars on day 1 to day 2 changes relative to you, right? So you got your angular change here, let's say whatever, 2 degrees, I don't know, right? That's called the longitudinal. And that fits. So Kepler, when he does his model using the real sun, the real apparent sun, he gets it all to fit the longitudinal within 2 minutes of error. It's perfect. It's like 2/60th of a degree. It's really good. But the problem is the latitudinal. It's called this arc here. Actually, it's from the Earth. Actually, he's using it from the sun. So from the sun, the latitudinal angles, that all of a sudden is now off way too much. It's like almost a quarter of a degree. It's way too wrong. All of the observations that are latitudinal are now wrong, right? So he's got one type is okay, but now the other one, the one that goes above and below, that's now way too far off. You can't accept that. So he goes back to the drawing board. He readjusts his model to make the latitudinal observations fit properly. So he does it. He gets the latitudinal observations to fit properly. There's a video on this, so don't be intimidated by the fact that I'm saying things that you probably don't have reference points for. But also, when he does that, what happens with the longitudinal observations are now all off by the same degree. So he adjusts and he adjusts and he tries to like give on one and take from the other a little bit, but no matter what he does, and he spends 5 years doing this, right? So this guy really is committed to truth, even though he knows this is wrong. Think about the quality of soul that this guy has. He butchered through this hardcore math for 4 years to get the thing to fit, and he can't break the 8 minutes of observational error. He can't get the thing to fit this 8-minute discrepancy. 8 minutes is really, it's like 8 minutes is like 8/60ths, which is like 1/5 of a degree. It's really not much. But he can't get rid of it. And so with that,
It's not much from close, but out there it's pretty big.
yeah, it's well, it's several thousand miles. So,
But it's still better than whatever has been done so far.
Yeah.
and again, I've lost some of my quotes, so that sucks. But oh wait, hold on. There you go. I lost my quotes. All right, so Kepler is now free. He's basically in jubilee, because now after all of these years, he's finally created an ontological paradox, a paradox that has no ability to be resolved within the formal system of circles and mathematical points. There's no solution, provably, so that nobody can present another model that includes those without being either stupid or dishonest after Kepler having done it the way he did it. So he creates no freedom for people to now introduce another false such model, even if it works to describe the observations. Now Kepler could have retired. He could have become rich, because his system, as much as it couldn't account for those little 8 minutes of arc, was the best system ever created. It was more perfect at predicting the future positions of the planets than any system that had ever existed before. Now that's huge. That was his posterity. He could have been like, all right, I've done better than any human being ever. Now I'm going to just sit back in luxury and wealth and let it ride. But he doesn't. Now he's free to begin his real investigation into what is really the nature of the principle causing all of the changes in the solar system. And this. And by going into an investigation of ellipses, which is the sum of the new astronomy, right? This is now, I'm just saying this, doesn't mean you know it, I'm just saying it. But by discovering now that ellipses do account appropriately for the retrograde motion, it accounts for all of the other anomalies that you see. Ellipses work really well. But now there's a whole new spectrum of data that he has available in front of him for the first time to continue on the hypothesis that he had since he was a kid, and that he writes about in the Mysterium Cosmographicum. Because every ellipse, oh, it's right here, every ellipse has the quality, unlike the circle, which involves a minimum and a maximum. In all the infinitely changing points on the ellipse, right? Because there's constant change happening at every moment of speed and of distance. Right? Every ellipse has that going on, right? Things are going to their slowest point. Like, you guys know where the slowest point would be if that's the sun, that's a planet at 2 positions. Where would be the slowest and where would be the fastest motion of the planet?
Yeah.
Where?
Slowest is the farthest?
Yeah. Yeah. And the fastest is the closest, right? All makes sense? Because you're more in closer proximity to the field of motion. So you have now something to work with, where everything in between is being organized by these extremes, so these minimum and maximums. So what Kepler's then able to do in the course of another book, which he writes over the course of like 12 years, which LaRouche has made the point that this has to be the base of our political movement. And when I joined in 2007, it was just beginning to become the basis of all of our organization's research, was the reading through of all of Kepler's works, starting from the Mysterium, where he first lays out his harmonic hypothesis, that there is something unifying all of the distances of the planets around the sun. And Kepler's first hypothesis, when he's a young man at 23 and he publishes this book, is the Platonic nested solids, those solids that Plato worked on to demonstrate a reasonable, rational basis for why the planet's orbits are where they are, instead of some other infinite, possibly conceptualizable position. Right? Are they where they are just because? Is it a circular reasoning? Or they are where they are because there's an actual reasonable reason for that. So his first model was that one, and it did a certain first approximation job, and he realized in the course of his investigation that the data he had been using when he was 23 was a little bit too off. So it didn't allow for the nested solids. Imagine each sphere here, each shell, being one of the orbits of the planets, all the way from Saturn. The known planets, right? They didn't know about Uranus and Pluto. But you got Saturn, you have Jupiter, you have Mars, you have Earth, you have Venus, and you have Mercury, right? All inside each other. That got him started. But it didn't work, ultimately. It worked on some of the planets, but it was a little bit too far off. It couldn't be forgivable if he kept holding on to that. Which is why he did his whole investigation on the new astronomy, to figure out, well, what is really going on? So he was able to pick that hypothesis back up after discovering the elliptical nature, because now, all of a sudden, he was able to look at the question that the Pythagoreans and Plato had been looking at, of whether there was a harmonic musical property in the orbits of the planets around the sun. And this had been dormant, so-called dead. This idea had been killed for 2,000 years in the Dark Age. And Kepler finally, Cusa actually talks about this, but Kepler proves it. Kepler takes Cusa's method, applies it, and demonstrates that this is the only way to account for what becomes the third law. That this is a very short, quick view of the thing, but as far as you can see here, I'm thinking everyone can notice that there's bars, there's measures here with several notes respective to each planet. You guys all see that? So you have here, based on the fact that the ellipse of Mercury is the biggest ellipse, it's so big that you could say that over 1 octave of notes can be found on it based upon its closest distance from the sun and the furthest. Whereas, Earth, which doesn't have, the highest note is, I actually don't know what that is. What is that? That's ancient musical strict. You know what that is?
It's a sol.
It's a G?
It's a sol, yeah.
Oh, it's a sol. Okay, so sol, la, sol, or la flat. So when you take all of your planet's motions and you put them on a common string, you can start now actually recognizing workable, intelligible melodies that are proven through a whole geometrical work that we ourselves have been working through in the new astronomy. So Kepler ends his work in celebration in Book 5, where he pulls it all together after creating a whole new system to give reason for the intervals of the musical harmonies on a string. He spends 100 pages working on developing a proof of what's the reason for the harmonies on an octave. He then comes back at the end of this book, at the end of Book 5, Chapter 7, where he says, "Thus it is no longer surprising that man, imitating his creator, has at last found a method of singing in harmony which was unknown to the ancients, so that he might play, that is to say, the perpetuity of the whole of cosmic time in some brief fraction of an hour, by the artificial concert of several voices, and taste up to a point the satisfaction of God, the Maker, in his works, by a most delightful sense of pleasure felt in this imitator of God, music." And LaRouche, in the same paper, it's called Cusa de Kepler, wrote his more developed thoughts on the role of science and music. Keeping in mind there's real political ramifications to this, where he writes, someone read this?
Should make it bigger.
Just get a bit closer.
Yeah, I'm sorry.
All of these factors associated with qualitative forms of increase of society's potential relative population density have the kind of net effect otherwise typical of valid discoveries of universal physical principles. Indeed, we have demonstrated experimentally that the principles of Florentine bel canto modes of choral composition and performance according to the J.S. Bach legacy have, as Johannes Kepler's work shows, a crucial significance as being effectively universal physical principles in the domain of astrophysics. Mathematics appears to be indispensable in physics, but without the principles of choral counterpoint defined by the work of J.S. Bach and the generation of Leonardo da Vinci earlier, there is a lack of the passion needed to move discovered principles of what are somewhat misnamed as so-called physical science into effective action. Every truly great classical artist and every truly sane scientist knows this from experience.
So, at the end of the day, the question becomes, what is it really about mankind that's worth caring about so much and finding precious enough that we would be willing to risk a lot of sacrifice, a lot of the potential comforts that we could have held on to, as Kepler had done, in order to fight to amplify and bring that out, to stop thermonuclear war, to stop the agenda of the oligarchy, which seeks to reduce the world population and bring in, effectively, what you can call another new dark age in the 21st century. Because if human beings, if we look at that population growth chart, and we believe David Suzuki when he says, humans are just maggots, right? That's how you know humans were different level of maggots, and that's the lesson of the population growth, then that's not really something you'd want to fight that hard to save, if we're just cancer cells multiplying, like Paul Ehrlich or Barack Obama's science advisor has called us, right?
We should all try and kill each other.
That's probably the best thing we could do for for the universe, is just end it, right? if that growth in population, qualitatively and quantitatively, is actually the shadow of something more divine and more beautiful, and it's a good thing when that happens, not a bad thing, then what would be that society that we would want to fight for to create and preserve and develop? So today, we could listen to a little piece of music. I think maybe JP might have a suggestion. I've got a couple, but we could listen to a couple of examples because Baruch is often hitting heavily that the music that we listen to, that we give our passion to, shapes our self-identity and shapes our ability to think critically in a time, not only of crisis, but any time in general. So our capacity to form judgments, to form a deep concentration span into processes that require deep thought, are affected, whether we like it or not, by the culture in which we live, the arts, the music, the entertainment. All of these things are the invisible forces which shape our self-conception and our power of making judgments of right and wrong and beauty and ugly. Because there's a lot of ugly ideas out there, right? And you gotta wonder, why do more people not actually judge an ugly idea for what it is? Because they don't have an inner standard of what is beauty. And you can't judge something false unless you know it's true. You can't judge something ugly unless you know it's beautiful. And that can't be there if you live in an ugly society which thinks that decay is normal and people are beasts, right? Or viruses at worst. So the idea of going to investigate in an honest way the real method of composition of great classical scientists like Kepler, people like Johannes Bach, who was able to make his breakthroughs because of Kepler's revolution in musicology and astrophysics. That's where the whole Bach revolution came out of. Bach's teacher was just worked through and translated a bunch of Kepler's works. Actually, he didn't have to translate them because he was German. But he worked through Kepler's works and carried this forth into Bach's world. And this gave birth to such people like Haydn, Mozart, Beethoven, Schubert, Schumann, Brahms. And Baruch has been making the point that this whole current, this evolution of a method was cut off at the turn of the 20th century when you had the unleashing of a series of insane, unnecessary wars by the British Empire, starting with World War I, the imposition with that pessimism in the culture that was brought in to create mathematics as a replacement for physical science. And people like Einstein and Planck, who made their discoveries self-consciously because they were musicians, and they tried to communicate this to a lot of people. This was numbed out of the scientific community. So very, very, very few scientists actually had the musical basis that Einstein and Max Planck had when they made their discoveries into the macro and into the micro universe that would help us break free of our sense perception even more.
It was attacked as being like traditional, not moving forward.
That's, yeah.
Like it wasn't even numbed out, it was like attacked viciously.
Yeah, because he said, why are we going to throw, Einstein and Planck were saying, why are we going to throw over Kepler? Like when yeah, sure, we discovered that there's new processes occurring that we can't explain in the atom, but why would we just throw out all of classical physics? Like I know Newton's bad, but like, it's like, why are we going to throw out everything? Leibniz and Kepler, why would we do that? And just create something statistical and mathematical with the Copenhagen school. Why would we just do that? We might be throwing the baby out with the bathwater. And he fought like hell to make sure that people didn't succumb to the idea that there's no truth, which is what Niels Bohr, Max Heisenberg, and all of these guys were saying, right? Because they were saying if you can't measure it directly, it doesn't exist. And since you can't measure a photon or an electron directly, you can't measure its position and its velocity directly, thus, it doesn't exist. It exists maybe as a probability wave or something. And Einstein never accepted that, Planck never accepted that, and since then, we haven't had any actual breakthroughs of principle since that time, except what Baruch has done.
Oui, mais Mathieu, encore une fois, le fait que l'être humain a pu mesurer justement, et c'est ce qui a permis justement de faire évoluer les sciences. Je veux dire, parce que si on partait de postulats un peu abstraits, mais que pratiquement on n'arrive pas à les mettre en œuvre, disons, ça n'aurait pas mené trop loin. Pour les mathématiques, la géométrie, la physique, la chimie, tout est basé sur quelque chose de palpable.
Oh, I have no doubt. I'm just saying that, are you saying, when you say palpable, do you mean like the discovery is palpable, or do you mean the
Un peu plus intelligible que justement ce discours-là.
Yeah, you know, there's measurement of ideas, but there's
Yeah.
physical world.
Nor am I
you
saying that you
measure
should. Yeah, I'm not saying.
centimeters.
Let me give you an example. You asked me before, like, what are these two?
general abstract.
Yeah. Okay, let's get out of the abstract, okay? Here's an example of something which today is being treated like it's fringe. However, the implications of this body of observations overthrows the standard model quantum mechanics that we're currently being told as scientists in universities to adapt to. It's premised on certain assumptions, right? Just like the old standard model of astronomy was premised on certain assumptions, so is the standard model today. There's a guy named Simon Schnoll, who's a Russian scientist. In the 50s, he had done some major pioneering work on chemical reactions with ATP, which is it's a molecule, as far as I understand, that helps move energy through your body, and especially it's useful for muscular reactions, right? Your whole body, if you didn't have this, would just not have any motion, you wouldn't have any muscular reactions, and you shrivel up and suffocate.
You said ATP?
Yeah. And then there's another one, anyway. And what he was observing was an anomaly that within every, if you measure all of the reactions of ATP over the course of a minute, and then you do the same thing over the course of the next minute, even if you weren't doing anything, you were just sitting there, it was always changing in an almost random way. So he was asking, is it really random or is there something going on? And what he did is he found a way of, over the course of many days and many months, he would look at all the reactions of ATP in many subjects, and he found that there were certain common spikes of reactions. So it seemed chaotic. However, there was a certain what's called fine structure, which was periodic. So every 30 days, every year, you had these common spikes in the periodicities that were, it was a sign that there's some unknown process happening. We didn't know what it was, but he knows that there must be some order above the seeming chaos that is shaping that. So what he did, after doing this not just with ATP, but he took many more biological molecules together, and he found that there was the same phenomenon happening. Like 20 different molecules, many different test subjects. He put them around different parts of the world and found that it doesn't matter where you are in the world, that will still happen. So he's like, well, let's compare this now to maybe something which everybody agrees is totally stochastic and random. Stochastic being just that which has no rational, there's no reason for it. It's statistical, it's intrinsically random. Something absolutely random. And he says, well, a place that everyone agrees is in atomic decay rates. So it's true at any sample of something radioactive, it's always giving off, beta decay or an alpha decay or a gamma wave. That's always happening in any radioactive, fissile material. Now the paradox with that is that the half-life of any radioactive substance is constant, right? Radium has like 200 million years. It takes that long, that period of time, for half of the substance to decay, to just basically become something else, right? And so every radioactive substance has a different half-life, but it's constant. It doesn't change. Some of them are 30 years, some of them are a few minutes, some of them are many more years. But while that's true about any substance, you can't predict where the next alpha or beta decay will happen. You don't know if that one atom that you're looking at is going to happen in a minute, or in a year, or in 30 years. You don't know. And so that's no matter what we did to radiation, to radioactive substances, by putting it into ultra cold, sub-zero Kelvin temperatures, super hot, hit with rock, whatever. Like, it doesn't matter. We put it into all sorts of extreme environments. It didn't change the rate of stochastic atomic reactions. So everyone agrees that this is a bedrock of modern quantum mechanics. The anti-Einstein quantum mechanics that we practice today. That's one of those core axes, kind of like the circle or the epicycle. It's that deep. And what he found is that when you do that, he was surprised to find that it's not actually that stochastic. It's the same 30-day cycles, the same year-long cycles occur in that, just as it did with the biological, like ATP and other like biomolecules.
For the radiation.
For the radiation, it's just the intensity was lower, but the same thing was happening, right? And so, in the course of an investigation, this brought him to look at astrophysics, and then he realized that the sidereal motion of the Earth and the real like the actual daily arcs of the Earth are in conformity over the course of the year and of a month with those reactions of our bodies, as well as of basic atomic substances. Which means, and why is this controversial, is because that means there's no wall separating classical so-called physics from quantum mechanics. That the same processes on the macro scale are on some level influencing and organizing those microphysical processes. The macro and the micro are actually operating on one common process. It's just expressing
it's random at the small,
yeah,
knowable in the large.
Yeah, that's the presumption, right? That they say, oh, classical mechanics says everything is predictable by formulas in the large. That's where you have, Newtonian gravity and things that we can just like predict with a formula. And then on the small, it's totally random, totally no reason, right? And since the whole is built up from a bunch of small things, thus the whole is being organized. The apparent order is being organized by a bunch of randomness, right? That overthrows. So that discovery is not acknowledged in modern science. He's attacked. There's like a massive inquisition for decades against this guy because the implications of the data, it's good measurements, it's good statistics, but the implications of reading it properly overthrows the entire priesthood, the whole structure of axioms needed to sustain.
In respect to this specific situation, mais pas toute l'approche scientifique.
The whole approach. It throws over the whole methodology of using statistical, mathematical methods. Yes.
It takes different forms depending on the subject, but the method is the same.
Well, yeah, you know what I'm saying, right? Like the question of God doesn't play. That's what Einstein was saying. He wasn't messing around. He was serious. Right? Like randomness is not what governs the universe.
You can have the facts, you can have the information. Many different people can have access to the same information, but if they don't have a hypothesis, and this is what real science is about, is if it were about data and just analyzing the mechanics of how something works, like looking at these seemingly random stochastic trends and whatnot, you wouldn't be able to deduce that there's something higher organizing all that. You wouldn't be able to explain why. But the question of real science is the question of causality. It's being able to say, why are things happening this way and not another? What's the unseen cause? And that's what these guys are actually looking at. This is what Kepler, his courage to discover what he did about why are the planets where they are. To this day, if you ask even like most NASA scientists and you ask them, why are the planets in the orbit that they are, where they are, they can't tell you because they haven't studied Kepler. They don't actually know. They know the formulas, but that doesn't explain why the planets are there and not somewhere else. So, they're limited. The real science at that level, which people like Kepler or like Einstein, where they're able to completely redefine how we think about the universe, most people can't do that today.
Poets and scientists around Erasmus, around Thomas More, around Francois Rabelais, who were organizing to crush the oligarchical principle in the 15th and 16th centuries, which is embedded in their poetry and their ironies and their stories that today people just don't know. They just don't know. So he's going to go through that. And then tomorrow at 1 o'clock, we're going to have a class by one of our science team members, Megan Beats, who did some of the pioneering work on Johannes Kepler. She's going to go through a class bringing up the question of the political implications of music in more detail. And we're going to have a class on what the hell happened in ancient Athens such that you had a society that loved truth, that was producing Plato's and Socrates, just to something that was going into a self-destructive death spiral of imperialism in a relatively short period. So what's the value of reading Plato? And for those who want to stay around for that, after the class we're going to read a Plato dialogue of the Meno. So obviously you're all invited to bring people. For now, I was going to suggest maybe we listen to a Riccardo Muti performance of Mozart's Ave Verum Corpus, which ellipses, which have two focal points, and thus, you can apply those formulas to calculate motions of planetary bodies in space. One of those focal points is the sun. He discovered that there's a quality we're usually told the second law. This is what, I'm just going through what we're told in school, right? This is not saying why these things are true. These are just saying what we're given, and then we're told to just memorize that and maybe use it if we go become mathematicians. He basically discovered that there's equal areas in equal times. So area, time. So if there's a certain given area swept out at the maximum distance, at the closest distance, over like a certain x time, and you take that same amount of time at the furthest point that the planet is from the sun, right? So I'll call this A and call this A prime. That same amount of x time that the planet sweeps out at the furthest, as you see it in the closest, that area of A will be equal. Okay, so this area will be equal to that area on the condition that this time is the same as that time. If that's true, you get equal area, equal time. And the third thing is something which we're not going to touch on so much in this presentation, but that in every planet, there's a square cube relationship. Now we're usually given these numbers as numbers. We're told like just add a little 3 or a little 2 on top of the number and you get the square and cube. Kepler doesn't think numerically. He uses that, but his point is always think physically. Think about actually the purpose of using volumes and squares to measure areas and volumes. Don't use cubes, right? Don't think of it just as being numbers. So
The notion of gravity.
Father of the notion of gravity, yeah. What did they usually give you when, I don't know if you remember back in school days?
They gave us formulas.
Formulas. It's 3 laws, right?
Is there the story about a apple?
No.
That was a guy 80 years after Kepler, who we've made the very provocative statement ripped off. It was actually a political plant to rip off all of the real discoveries that Kepler made, and Leibniz made, and Huygens made, and Bernoulli made before him. That guy's Isaac Newton. There's a big myth around him being this like godly, like universal genius who discovered everything through empiricism and mathematics and didn't use his. He actually put out a law of mind saying that if you want to make discoveries like me, if you want to be as great as I am, you just can't make any hypotheses. You just use your senses. You make formulas to describe what your senses tell you, and maybe you'll get it kind of approximately right. Now, if you actually adopt that method and use that, because it's so great, you want to be great and make further discoveries. If you actually adopt that method, you're actually not going to make any more discoveries, which is something which we can go into.
It could be said that the only time Newton really used his head was when he received the apple.
Yeah, there's a rotten apple there. Let me just write on the board. I guess I'll just write. So just what we're given is the shell, right? We're given the 3 laws. You remember what those 3 laws are? Kepler's formation. They're basically formulas associated with describing ellipses, right? He's the guy, after all we know, was the first to conclude that planets don't travel around perfect circles. They travel in the form of an elliptical shape around the sun, right? So there's certain formulas associated with. You guys know where the word Renaissance came from? Rebirth of what?
Well, it means rebirth. But the only way for something to be reborn or reborn again is had to be dead first.
So ironically, you could say that.
Yeah.
But what was being reborn? What had so-called died such that it was then reborn in that period?
Generally, like science or our notions of science, I guess, and how we thought of each other and like human beings.
Fundamentally, there's a core idea of human nature that was embedded in Socrates and Plato, in the greatest science, that had been lost for over 1,000 years after Athens went into an imperial mode and shut down its appreciation for the ideas of Socrates and the ideas of the school of Athens. When it had been taken over and was subjugated to its own self-destruction by losing a love of truth, the whole of human civilization went into effectively a dark age. Great revolutionary ideas didn't really happen, except at a certain point in Islam, you did have a grouping of humanists who did tap into that, revived this lost idea, gave birth to it, and through this process you had people like Cusa, who, coming from Europe, from Germany, was living in a world of complete oligarchical terror. There was just Eastern and Western churches killing each other in civil wars, and all being funded by the same Venetian bankers for hundreds of years. That was the way of life in the Dark Age. It was just literally constant death through famine, disease, the pest, and war. And for what laws govern their own society. The idea of self-organized nation-states came out of this fight. And it wasn't just given to us by an oligarchy that wanted a new challenge because they were getting bored and it was too easy to control people. So, what LaRouche stated in a somewhat recent paper in 2007, when describing this process that I'm going to unfold, he said, for modern civilization, the first crucial experimental test of Cusa's principle for the modern practice of physical science as a whole came with Johannes Kepler's uniquely original discovery of the principle of universal gravitation. The significance of Kepler's discovery of this principle of experimental method and his ensuing discovery of the harmonic composition of the planetary orbits typifies the notion of universal principles which should have guided modern European science thereafter. So that's a lot for one sentence, or two sentences. But this is going to become a lot more clearly developed. I'm not going to go through the full implications of Kepler's discovery, but I'm going to go through some elements of this. First of all, I know people didn't know Cusa, but do people here generally know Kepler, Johannes Kepler? Heard of the name? Of course. You heard of Johannes Kepler?
Yeah,
A little bit? Eve? Yeah, of course. Yeah. Okay. So what do you guys know of Kepler? What do you know when what do you associate with the word Johannes Kepler?
Just what's told.
Just what I told. Okay. Eve, what do you know of Kepler?
That he was the father of...
A lot of ignorance, like Christine went through at the beginning of her presentation. So when Cusa actually went and organized in Constantinople, he discovered that within the matrix, the cultural matrix of the Islamic Renaissance, there was this breadbasket, this amazing discovery of this lost method of thinking that had the idea that man was not an animal or a worm to be, whipped for causing a dark age. There was an idea that there was actually something divine within every human child. And this is something that he and a network of co-minded thinkers brought back and made the struggle of educating the orphans, of creating an idea of natural law, that every human being, regardless of race or gender or whatever, had the capability of discovering universals and applying those discoveries to improving the lives of themselves and their fellow men, both now and into the future. So, Cusa was a major, most people here probably I didn't hear about Cusa. I'm guessing people who haven't already been around the organization, I'm guessing people have not heard about Cusa. Am I wrong in assuming that people who have just come here for the first time have not heard of Cusa? Nicholas of Cusa? No, probably, you haven't heard of him, right? No. Me neither. And this is probably yet still, like LaRouche makes the point that Cusa, along with Brunellesc, gave birth to modern science, the modern nation-state system, the idea that the feudal will of the oligarch, of a lord or a monarch, is not legitimate to rule the masses. Right? That everybody has within them the ability to, because they can discover the laws of creation, they also have, when they discover those laws, when they're given that opportunity to develop themselves, the ability to judge and give consent